Hello and welcome back to Calculus 1, section 3.10 on derivatives of inverse trigonometric functions. So before we run into the inverse formulas, I will remind you of what an inverse means. So first, you have that y equals f of x, where x is the input and the y is the output.
Right?
What happened?
That's one typically a function. When you put an x, that'll give you y. An inverse function takes that y and makes it back into x.
Yes. So what you do is you swap x and y and you can compute the inverse function. So inverse function of y will give you the x back. So that will be the output, will give you the input. Graphically, we can have the domain and the range, and then you have a x element and y element. So now the function will turn x into a y, and the inverse function will turn y back into x. Now, not every inverse is a function, so we have to be very careful about that. And I'm going to jump now into trigonometry, because these are trigonometric functions, and work on that one.
So not every inverse is a function?
Not every inverse is a function, exactly. We'll see that now. So what we know is that, let's say, sine of pi over 6 is 1/2. Sine of 30 degrees or pi over 6 radians is equal to 1/2. Now, the inverse sine of 1/2 is pi over 6. So inverse sine of 1 over half. So technically, sine of an angle is a number. Inverse sine of a number gives you an angle. Something to keep in mind.
I'm sorry, so,
Trigonometric functions. What happened?
alright, so what is the symbol on the top next to sine, if I might ask? Excuse me.
What symbol?
Sine. It's a symbol for angle. Angle. Oh, yes. I'm familiar with that. Sorry for the interruption.
So now let's talk about this issue of inverse not being a function and how we fix that. So consider function y equals sine x. It is an infinite wave going on to positive and negative infinity and stretching up as 1 and negative 1 on y. Now, if you are to find the inverse function and graph that, y equals sine inverse of x, what you get is this wave which goes up and down. Now, clearly, this is not a function because it fails vertical line test. So not a function. So now we need to fix this in order to be able to use it. So let's fix it. What we do is we restrict the domain. So it passes horizontal line test. vertical line test is for functions, the horizontal is for inverse functions. So if I cut the sine function like this, from negative pi over 2 to positive pi over 2, you would see that this one will pass what we call horizontal line test. Because horizontal lines will cut this function exactly once everywhere. Now, if it passes horizontal line test, that means that the inverse will pass vertical line test and be a function. So now, if I draw the inverse, so this is sine x, and now I'm going to draw sine inverse x. So if I draw sine inverse, we are going to have this situation, and you see that this little piece passes the vertical line test, so it is a function. So we took something that was not giving us, took a function that was not giving us inverse function, and restricted the domain in such a way that we actually get the function. So now we say that y equal sine x on interval negative pi over 2 to pi over 2. You can say on. So y equals sine x on interval negative pi over 2 to pi over 2 will give us the inverse sine inverse x, and that one is on interval negative 1 to 1. And now you do this with all other trigonometric functions. Now, probably the most important out of all 6 is going to be inverse tangent. And you will see this function in many different capacities through Calc 2, Calc 3, differential equations, and so on. So if you are taking these courses in the future, make sure that the story of inverse tangent makes sense. So y equals tangent x is going to give you infinitely many of these squiggles. And if you are to find an inverse tangent, it will not be a function because all of these would be stacking on top of each other now, right? Just like sine was kind of turned 90 degrees, this would also rotate 90 degrees, and it would just be an infinite stack. Now, infinite stack, that's not really good unless it's pancakes, right? Then it's good. All right. So now what we do is, instead of having all of this, we are going to say inverse tangent x on negative pi over 2 to pi over 2. So we are going to chop it up the same place where you chop the sine. You don't chop the same all other functions on this. Some are chopped on 0 to pi, like cosine and secant and cotangent. They're 0 to pi. So now the inverse, so this will give us the inverse tangent graph, so tangent inverse of x. And this one is actually on negative infinity to positive infinity. So this is what it looks like. You have now horizontal asymptotes. The inverse tangent comes in, goes through the 0, and follows the other one. The values are pi over 2 and negative pi over 2, and obviously x-axis goes to positive and negative infinity. So this is what the graph of inverse tangent would look like. And now if you look at the inverse tangent graph, clearly you can draw tangent lines everywhere, so you should have derivative and all that good stuff. So now finally let's write the 6 inverse derivatives. So for this tangent, or for the trig functions.
Sine.
So we do the sine inverse.
Yeah.
So the derivative of sine inverse of x, 1 over square root of 1 minus x squared.
It's the x squared, not the radical, right?
Yeah. If it's radical squared, then they cancel.
Of course.
So now we have, the next one would be the tangent. So inverse tangent, the derivative of inverse tangent is 1 over 1 plus x squared. By the way, these are the two formulas that are used pretty much all the time. I don't even know if I saw the other ones ever used, unless it's a math exam. But for future math courses and engineering stuff, these two are meant.
I saw in the textbook for inverse sine x, it had a domain was between -1 and 1.
Yeah.
That doesn't apply to tangent x, or would it be?
No, it's infinities. I wrote it.
Oh, yes, I see.
And then I have the secant inverse x, which is 1 over absolute x square root of x squared minus 1. Now I will write the other 3 on a side, and you will see that remembering the other 3 is actually very easy, because they will have exactly the same formulas as the ones on the left. They just have minus signs, all of them. So they're really cool. So you just write, you copy everything and just put the negative. So instead of 1 over square root, you have a negative 1 over square root. Now we have a cotangent inverse of x, and that's going to be negative 1 over 1 plus x squared. And the derivative of cosecant inverse of x is going to be negative 1 over absolute x square root of x squared minus 1. So these are your 6 inverse trigonometric derivatives. And now the standard stuff applies: product rule and chain rule and quotient rule and tangent lines and all of the beautiful things that you enjoyed, right? We can do with these as well. So say you have the derivative of x squared cosine inverse of, I don't know, cosine inverse of x cubed, whatever.
Professor, is that the absolute value times the radical, or is that the
Absolute value, yeah.
Yeah.
Times, yes.
That's not like the root value.
Yeah, so it's not the absolute
Oh,
value.
no.
Okay.
Absolute value of x times, yes. So, what do we have? Well, if you look carefully at this, you have product rule. Here's your function 1, and here's the function 2. So we have our f and our g, and we do the product rule. Copy the first times derivative of the second. That's going to be negative 1 over square root of 1 minus x squared. So that's the derivative of, but then it wasn't x squared, it was x cubed, so this needs to be x to the 6, and then we have to multiply by 3x squared chain rule because of the it's x is cubed, plus cosine inverse of x cubed, it's a good effort, and then 2x. So the total over here is 3x negative 3x to the 4th divided by square root of 1 minus x to the 6th plus 2x cosine inverse of x cubed. So our original problem formula had x, but the problem has x cubed, which means we have to use chain rule. So when you are doing the formula, instead of writing x's, you have to put x cubed, but this x was squared, so x cubed squared is x to the 6. And then multiply by the chain, and the chain is whatever the guts were, right? And that's x cubed, so 3x squared. So copy the first, derivative of the second, plus copy the second, derivative of the first, which is 2x. And then you make it pretty. Let's take a look at another example here. Say well, how about something from homework? So wonderful. Problem 23 is looking for the derivative, they do in respect to z, so whatever. Derivative of cotangent inverse of square root of z. Now I'm going to write the function and then the modified function for the derivative. See, the formula you learned is that derivative of cotangent inverse x is negative 1 over 1 plus x squared. But this x can be actually any function. Doesn't have to be a function x. Can be anything. Could be a to the x. Could be square root of x, right? So, better version is the derivative of cotangent inverse of f of x, which means you can plug in anything you want in this cotangent inverse. And that changes the derivative.
That would be root z, correct?
Well, eventually. So we have negative f prime of x divided by 1 plus f of x squared. So if we replace x with any function, then the chain rule kicks in, and your x's are replaced by f of x. So that's why your x squared became f of x squared. But you also see that in the numerator, you no longer have 1. Now you have f prime, and that's because of the chain rule. So when you realize now that your f over here is root z, then following the prescription over here, you can quickly come up with the answer. So what's the answer? The derivative is equal to? Yes, so we have a negative, and then this should be the derivative of root z. Well, maybe you memorize, maybe you're not, but it's 1 over
2 root z, right?
2 root z, yes. Divided by, and we have 1 plus, and now it's original root z squared. And now you make it pretty. You have negative 1 over 2 root z divided by 1 plus z.
Yep.
And you can put over 1 to make it a double fraction. So now it becomes negative 1 divided by 2 root z times z plus 1.
How do we do that again? Multiply the...
2 that are far apart, and that goes in the numerator, and 2 that are close by, it goes into the denominator.
Alright, so you get 2 bar ones going to the numerator. I'll need to ask further about this. Should we try to distribute with this one into the...
You can write 2 fractions and divide them, it's okay.
Alright.
So these are our 6 inverse trig derivatives. Make sure that you are really good with the first 2, because they will show in your future courses. Calc 2, Calc 3, differential equations. The other ones, I really haven't seen them. I can definitely make the problems with them, but
Do you mind leaving that list up there for a moment? Or is there something else that has...
that's it, we're done.
Mind if I just look at
Oh, the formulas, the 6, these ones?
figure best to get after that now or later?
All right. See you all when?
Monday.
Monday, okay.